In this video, we're going to be going over how we can take the problems we were previously solving with convolution and solve them instead with Laplace analysis, but specifically how we can handle these discontinuous functions with shift theorem. Shift theorem says that if we take the inverse Laplace transform of a function f of s multiplied by e to the negative as, the inverse transform is going to return that function f time shifted by t minus a multiplied by a step function time shifted by t minus a. Now, the goal of what we're trying to do with these kinds of problems is, given the impulse response of a system, h of t, and a given input to the system, x of t, find the output of the system, y of t. Now, in convolution, we were convolving x of t and h of t in order to find the output y of t. Another approach to get the same result could be instead to find x of s, the s-domain representation of our input, and multiply that by our transfer function, h of s. And the result of that is going to be the output of our system, y of s. Now, this is still an s-domain, but if we take the inverse Laplace transform of y of s, this will result in y of t. And this allows us to get the same result using Laplace analysis as opposed to convolution. The first step in this kind of problem is to take our discontinuous time domain input and describe it with step functions. Now, if you notice, this input signal starts at -1, it goes to a value of 10, and goes back to 0 at t equals 4. So we can describe this graph as vi of t is equal to 10 u of t, our step function, but time shifted so that our function turns on at -1. So we're going to write t plus 1. So that way, when t is equal to -1, our step function evaluates to 0, and we get this part of our graph. Now, the next thing we need to do is describe our graph going back to 0 at t is equal to 4. So we can do that by subtracting another step function with a magnitude of 10 time shifted as t minus 4. Now that we have an equation for vi of t, our goal is to move this into the Laplace domain. The Laplace transform for a normal step function, u of t, is going to be 1 over s, but now that both of these two terms are shifted, we have to apply shift theorem. Based on our shift theorem, we can write the s-domain version of our input as vi of s is equal to 10 over s e to the positive s minus 10 over s e to the negative 4s. And now we can move on to writing the equation for h of t. Now, the slope of this line is 10 over 10, so we know that the slope of this line is just t. And we have a step function because it's 0 until t equals 0, and then the slope begins. So the first term of h of t is going to be h of t is equal to t multiplied by u of t. Now, when t is equal to 10, our slope levels out. So we have to subtract the same slope from our h of t equation. But we also have to time shift it to t is equal to 10. So for this part, I'm going to subtract t minus 10, u of t minus 10. And this is going to stay constant until we hit 20. And then again, we're going to begin sloping down. And if we look at this slope, it decreases by 10 over a span of 10, so we have a slope of negative t, but we have to time shift this up to 20. So we will say minus t minus 20, u of t minus 20. Now at t equals 30, our slope levels out again, so we have to add another slope of t, but time shifted, to level out the output of our graph. So we will add plus t minus 30, u of t minus 30. The Laplace transform of t is going to give us 1 over s squared. So now everywhere I have a t, I have a 1 over s squared, and we'll be applying the time shift theorem to these terms. Beginning with our first term, we have 1 over s squared minus 1 over s squared e to the negative 10s minus 1 over s squared e to the negative 20s plus 1 over s squared e to the negative 30 s. And this equation is now describing our h of s. The next step to find our output is we need to multiply h of s times our input, vi of s. And that'll be equal to our input multiplied by h of s. And if we expand out these terms, this is what we are left with. And this is our output in S domain. So the next step is to apply shift theorem again in the inverse Laplace transform of each one of these terms to find the output as a function of time. If we take the inverse Laplace transform of 10 over s cubed, this gives us 5t squared. And if we notice, each of our terms has 10 over s cubed in it, but is time shifted by a different value. So we'll go through next and find the inverse Laplace transform of each term and appropriately apply the shift theorem to it. Beginning with the first term, we know that 10 over s cubed is 5t squared, but applying the shift theorem, we have 5t squared, so we'll write t plus 1, shifting it, and then squaring the term, and then attaching u of t plus 1. Now the next term we are subtracting, so we'll say minus 5t minus 4 squared, shifted by u of t minus 4, minus 5t minus 9 squared, shifted u of t minus 9, plus 5t minus 14 squared, u of t minus 14. And now we'll move over to our next line to continue with our next term. So we'll write minus 5t minus 19 squared, u of t minus 19, plus 5t minus 24 squared, u of t minus 24, plus 5t minus 29 squared, u of t minus 29, and finally minus 5t minus 34 squared, u of t minus 34. So now what if the problem asks us to find the output for t equals 11? Now the only terms of this equation that we're going to have to deal with are this term, and this term, because our other step functions are going to evaluate to 0 for time is equal to 11. So if we plug this value in, the output is equal to 5 times 12 squared minus 5 times 7 squared minus 5 times 2 squared. And evaluating this gives us our output at time equals 11 as 455.